This is a video solution to tutorial sheet 3, which is this one here. This is tutorial sheet 3 entitled R session. So this is the second tutorial involving R. Okay. So I'll go through this command by command, and I will also do the 3 exercises at the very end of this tutorial sheet. Okay, so let's begin. Okay, the first thing you need to do is to open the R window. You should know how to do this from the first tutorial that we had. Right? All right, the first thing we're going to do is to create a vector that contains the following numbers. So this is a vector X that contains the numbers 3, 22, 5, and 7. Right, then I'm going to illustrate the rep command. REP stands for repetition, a short for repetition. So you should say rep X times 2. It produces this. So what it does is it repeats the vector 2 times. So you have 3, 22, 5, 7, 3, 22, 5, 7. Okay, now you should do this. This is slightly different. What happens is it repeats 3 one time, 22 2 times, 5 2 times, and 7 3 times. So you get this 3 one time, 22 2 times, 5 2 times, and 7 3 times. Right, the next I'm going to show you is length. So what it does is it repeats X enough number of times so that the total number of data points is equal to 8. So 3, 22, 5, 7, 3, 22, 5, 7. So you have 8 data points. So it repeats, the 8 here represents the total number, the total number in the data in the output. Right? Next, this one. Okay, here it repeats each element of the data set 3 times. So 3 repeated 3 times, 22 repeated 3 times, 5 repeated 3 times, and 7 repeated 3 times. Okay, next. Okay, here what you have is you have the numbers 1 to 3, right? Repeated 2 times. So you have 1 2 3, 1 2 3. Okay. So here you have the numbers 1 2 3. Each number is repeated 2 times. You have 1 1, 2 2, 3 3. Here you have this. So here, this one, as this one is a vector containing the numbers 1, 2, and 3. So 1 is repeated 1 time, 2 is repeated 2 times, and 3 is repeated 3 times. Okay, now an example involving characters. So suppose this is a vector with 2 letters A and B, right? And I'm going to repeat A 2 times, B 3 times. So you get this, A repeated 2 times, B repeated 3 times. All right, okay, that's on rep. The next command I'm going to talk about is sequence. The short is SEQ. SEQ is short for sequence. There are basically 3 things you need to put: from, to, and by. So when you type this, you get all the numbers from 2 to 8 in steps of 2. So it's 2 plus 2 is 4, plus 2 is 6, 6 plus 2 is 8. Okay, you can also type this without the words. You will get the same answer. So you have the same output, 2, 4, 6, 8. Okay. Now, if you do this by 3, then you get 2, 5, and 8. 2 plus 3 is 5. 5 plus 3 is 8. If you do it by 3.5, then you get only 2 numbers, because 2 plus 3.5 is 5.5. 5.5 plus 3.5 is 9, which is beyond this range. So therefore, you only get these two numbers, right? Next, next one is from 5 to 2 in steps of minus 0.5. So here you have a decreasing sequence starting from 5, going down to 2 in steps of minus 0.5. So it's 5, 4.5, 4, 3.5, and so on until 2. Next, you have from 2 to 8, and length out is 6. So what this means is that it's a sequence of numbers starting from 2 until 8, but there should be 6 elements in this output. So it's basically a sequence of numbers from 2 to 8 that are equally spaced, and there are 6 of them, right? So as you can see, the distance between any two successive numbers is the same. So 2 plus 1.2 is 3.2, plus 1.2 is 4.4, plus 1.2 is 5.6, and so on. All right? So the length here represents the number of data values to output. Wow. Okay, next, suppose you type this, right? Then that represents all the values from 1 to 5. Now, if you say from 4 to 14, along with Z, you will get this. So here, what you're doing is you have a sequence of numbers, right, from 4 to 14, right, and there must be 5 of them because Z has 5 numbers, right, and they must be equally spaced. So as you can see, from 4 to 6.5 is 1.5. You're adding the 1.5. If you add 1.5 to 6.5, you get, sorry, 2.5. From 4 to 6.5, you're adding 2.5. If you add 2.5 to 6.5, you get 9. If you add 2.5 to 9, you get 11.5, and so on. Right? Then this command just simply gives you the numbers from 1 to 4, whereas this command gives you the numbers from 4 to 1. Okay. All right. The next thing I'm going to talk about is some summary statistics. Before I do that, I need to read the Moses data, which I talked about in the tutorial sheet 1. So let's go to the course website, which is this one, week 3. This is week 3. So let's look at the Moses data, which is this one. So this is the Moses data that has the time column. So I want to read this data, so I copy the URL, right? Go to the R session, paste it, right? Then I want to read the data, so say read table, the URL, and I don't want to read the header, so I say header equal to true. Okay. And I need to give a name for the data. Let's call it Moses. Right now, if you type Moses, you see there are two columns. The first is the counter column, you can ignore. The second is the data column, which is called times, right? Now, if you type names of Moses, it will give you the named column, which is time. Right? All right, now let's call this, just for short, instead of typing Moses $time every time, just let's call it T. So T contains the data values, right? Okay, now let's do some summary statistics. So the mean of T is this, the median of T is this, the variance of T is this, the standard deviation of T is this, and the this command 5num, which means 5 number summary of the data, which is T, is this. So it gives these 5 numbers, which are, the first number is the smallest data point, the second is the first quartile, the third is the median, the fourth is the third quartile, and the fifth is the largest data value. So let's call this F and S for short, okay? So suppose you want to compute IQR. Remember, IQR from the notes is the difference between the third quartile and the first quartile. So the third quartile in this output is the fourth element, right, of the output. The first quartile is the second element of the output. So you have as IQR as being equal to 1.05. Right, and another way to summarize data is to use the command summary, and it gives you this output: the minimum, the first quartile, the median, the mean, the third quartile, and the maximum. Okay. Now another way, well, this time to compute the quantile or quartiles of the data is to use the command called quantile, and then you put the name of the data, which is T, then you say probabilities and the levels of the quantiles that you want to compute. So 0 corresponds to the minimum, 0.25 corresponds to the first quartile, 0.25 corresponds to the first quartile, 0.5 corresponds to the median, 0.75 to the third quartile, and 1 corresponds to the maximum. And there's also something known as type, and I will always choose type to be 6. There are other types one can use, but you don't need to know this for this course. Always use type 6, right? Corresponds to the formula that I given you in the notes. So if you return, this is what you will get. So 0, the probability of 0 corresponds to the minimum, which is this, same as what we got earlier. Right, this is the first quartile, median, third quartile, and the maximum. Right, so these are the same as the values that we got under the 5 number summary. Okay, so that's a useful command to know. That is the quantile command. Well, the next thing I'm going to talk about is some graphical commands. Now, suppose you want to record everything that you're typing or plotting, right? Then you can use this command, Windows in brackets record equal to true. So anything that you do afterwards, after entering this command, will be recorded, right? Including the output and so on, right? So I don't want to do that, okay? Now, suppose you want to open a device for plotting stuff, plotting things like, I will show you later on what kind of things you can do. So if you issue this command, it will come up with this window, right? This is a graphic window and it has a number. It says the number here is now 2, right? Okay. Now, if you said, so if you issue this command, a device set 2, right? So it sets the device 2 to be active right now, right? And you should say device off 2, then it makes it inactive. As you see, it disappeared. The thing that the graphics window just disappeared, right? When I issued this command, right? Okay, the next thing I'm going to talk about is bar plots. Bar plots are used for plotting categorical data. So let's go back to one of the data sets that we talked about earlier. You may recall this, the party data set, where you have 5 different parties: conservative, Labor, Liberal, Democrats, UKIP, and others, or other, right? These are the 5 parties, and let's repeat each of these the following number of times. So I'm going to use so conservative, say, repeated 369 times, Labor 314, Liberal Democrats 75, UKIP 118, and the other 124. All right. So now if you type poll, you see this is the data set that we just created, right? By using the rep command. Okay. Now let's turn this data into factors, right? The factors being the 5 different party names, right? Now if you say table of poll, this is the summary that you get. So you get the 5 different parties and the number of seats each party got, right? Now if you say plot, excuse me, if you say plot, this is what you will get. So here in this is known as a bar plot. So the length of each bar corresponds to the number of seats. So conservative have 369, Labor has 314, and so on, right? So this is a very useful plot for representing categorical data, right? Like, okay. All right. The next thing I'm going to talk about. Before I go to. Yeah, all right. The next thing I'm going to talk about is histogram, right? Histogram is used to represent continuous data. So suppose you may remember T is the time data from Moses, right? Now suppose you want to do a histogram of this. It will look something like this. So here you have on the x-axis, you have the intervals for the time taken to be 47 to 47.5, 47.5 to 48, and so on. And on the y-axis, you have the frequency. So for example, there are just over 10 data points between 47 and 47.5, just over 20 data points between 47.5 and 48, and so on, right? You can do a hist command with the frequency equal to false, and that will produce something like this, which is similar, but the difference here is that the y-axis is a density. It's no longer frequency, but it's a density. And you should know from probability 1, which you took last semester, that one property of density is that the area below the histogram must be 1. So if you sum all these bars, it must be equal to 1, right? So that's a property of the density, as you know. Okay. And the x-axis here can be changed as you wish. So for example, there's a command called breaks you can use. Right, so if you use this command, I made a mistake, sorry. It should be sequence, not, all right. So if you use this command, what you have here is the x-axis has changed to from 47 to 51 in steps of 0.4, right? You can also change it to anything else you like. For example, you can have from 46.8 to 50.8 in steps of 0.4. So here, the limits of the x-axis are from 46.8 to 50.8 in steps of 0.4. Right, that's on histogram. The next thing I'm going to talk about is box plot. Now let's take the data on T again. This is a box plot on the times data, right? So you see the middle line, the thick middle line is the median, right? This is the first quartile, this is the third quartile, and so on. I mean, I explained what a box plot is in the class. I made one of the videos, right? Okay, next thing. All right, before I proceed further, I want to go back to the website and read one more data set. So let's go back to the website, course website, and let's read the runners data set. Right here, you have two columns of data. The first column is Pmol, which represents the concentration of a chemical in the body. And the second column is a group column. It is either successful or collapsed. So either the runner was successful or the runner collapsed, right? So let's first read the data, copy the URL and paste the URL here, right? We have read.table header. You don't want to read the header, so you say header equal to true. And let's call this runners, okay? So this is the data that you have, runners. Okay, you have, as you saw earlier, there are two columns of data except for the first column, which you can ignore, right? So the names of the two columns, which you use the names command, right? Pmol and group, right? Okay. Now suppose you want to do a box plot of the concentration level versus the group. So you say Pmol, then this tilde key followed by group for the data runners. And this is what you will get, right? You will get two box plot, one for the collapsed group and the other for the successful group. And you can see clearly that for the collapsed group, the concentration level is much higher, or is a lot higher than for the successful group, right? And so is the variability. The variability of the concentration level is also higher for the collapsed group compared to the successful group. Okay. Remember, the variability is the width, is the length or the width of the box here, right? Okay. Now suppose you want to take a subset of this data such that the concentration level is greater than 100. So these 7 data points here, each has a concentration over 100, right? And suppose we want to select that subset. To do that, you will use the following commands. The first, you define high concentration to be the Pmol greater than 100. Okay, and then you define runners with high concentration as a subset of the runner's data set, where the subset corresponds to, so the subset corresponds to the high concentration. All right. Now, if you type runners high, this is what you get. You see, this is the subset that we wanted to select. Okay, now you should do a summary of the group corresponding to this subset. This is what you get. You have 7 people, 7 runners here. All of them have the group name equal to collapsed, and 0 of them have group name equal to successful, right? Okay, so in this case, there's no point having this because all of them have collapsed, right? So you would like to actually, get rid of the successful thing. And one way to do that is following. One way to do that is to use the command drop levels, right? Okay. Now, if you do the summary now, you will see that this level has been dropped now. So you just have seven runners having all of them collapsed, right? Okay. So that's on that. All right. The next thing I'm going to talk about is scatter plot. Scatter plot is something very easy to do in R. So suppose you take the numbers from 0 to 5. So these are the numbers from 0 to 5 in steps of 1. Now, suppose you want to plot x squared versus x. This is what you will get. So what I have done is to take the square of the values from 0 to 5 and plot them versus x. You can also do this and you will get the same output. There's no need to put x equal to or y equal to. You will get the same output. Now, this is like a parabola, a half parabola. If you want to see a full parabola, you take the numbers from -5 to 5, right? And then do this plot, right? You see now, you see a full parabola right over here, okay? All right, and then another plot is to, suppose you take the sequence from 0 to 5 with the length of 100. So what this means is that it means between 0 and 5, you want to have equally spaced 100 numbers equally spaced between 0 and 5. So this is what this command here does, right? Then you can use the plot command one more time, right? With type, I will explain what this is in a minute. Type equal to L and color equal to 2. It will produce this line here. So here type represents the type of line. L stands for line, right? And color 2 means red. You can change the color to, like, suppose you want 3, it will give you green, right? If you take it to be 4, it gives you blue. You take it to be, say, 6, it gives you pink, and so on, right? So different numbers correspond to different colors, right? You can also use the command lines right? So the lines command, it has the same effect as a plot command. So here I have plotted x cubed versus x using the color 4, which is blue, right? Okay. So that completes the tutorial sheet 3. We got up to this now. So the next thing we need to do is to do the 3 exercises. So I'm going to start with exercise 1, which is first we need to read the data set in this link, right? And there are 100 of them, and then do summary statistics, histograms, and box plots, and comment on their shapes. All right, so let's go back to the website, right? So this is the simulated data set, this one. There are 2 columns. The first is just a case number, and this is the simulated data. So I copy the URL, go to the R session, and paste it, right? So I'm going to read this into using the read table command. So read.table, and we don't want to read the header, so say header equal to true. And let's call this data sim data. Okay. So if you now type sim data, you will see the data that we just read. Okay. All right, and now the names of the columns are, you can just, these are the two columns that we just read. Okay. If you want to pick, if you are interested in the simulated data column, which is this one, right? So just for short, let's call this XS, right? Let's call it XS just for short. Okay. Then we can do summary statistics of the simulated data. So for example, the 5-number summary. This will give you the 5-number summary. Right? So the first number is the minimum, the second is the first quartile, the third is the median, the fourth is the third quartile, and the fifth is the largest value. So let's call this FNS. So FNS is this. Now, if you want to compute the interquartile range, that's the difference between the third quartile, which is this, and the first quartile is this, right? So this is your IQR. Another way of summarizing the data is just to use the summary command. Okay. And that will give you these numbers. So this is the minimum data, the first quartile, or quartile, median, mean, third quartile, and the maximum data. You can use the command var to compute the variance. You can use the command sd to compute the standard deviation. And you can use box plot. All right, so this gives you the box plot of the simulated data. You can see that the middle line, which is the median, is approximately halfway between the first and the third quartile. So it suggests that the data is kind of symmetrically distributed, right? If it is halfway, if the median is halfway between the two, right? Okay, so that's the box plot. You can also do a histogram. So this is the histogram where the y-axis is the frequency. And so it's basically counting how many data points lie in each interval on the x-axis. Right? You can also, if you change the frequency to false, then you get this where the y-axis is the density. So in other words, the area covered by the histogram must be equal to 1, as you know, right? And the x-axis can be changed as you wish by using the breaks command. So breaks sequence, say from 6 to 16.5 in steps of 1.5. Okay, it will produce a plot like this. So the x-axis goes from 6 to 16.5 in steps of 1.5, right? And here the x-axis goes from 6.25 to 15.25 in steps of 1. So you get a plot looking like this. So the x-axis goes from 6.25 to 15.25, right, in steps of 1. The kind of picture that you get, it looks kind of a bit skewed, but not too much. So you can say with confidence that it's approximately symmetric. So the data might have come from a symmetric distribution, like, for example, the normal distribution is a symmetric distribution, right? Okay, so that's exercise 1. Now let's go to the next exercise. Let's go back to the tutorial sheet. So this is the exercise number 2. So this is the Giese data set. It has 3 variables: day, duration, and interval. The variable that we are interested in is the duration variable, that which corresponds to 222 eruptions of the Old Faithful Giese in the Yellowstone National Park in the United States. The question is similar, so it's to compute the summary statistics, histogram, box plot, and comment. All right, so the first thing we need to do is to go to the course website and read the data set. So this is the Giese data set. So you see these 3 variables. We are only interested in the duration of the Giese, right, of the eruptions. So copy and paste, right? All right, and let's call this Giese. All right, so now if you type the name, you see the data. So this is the data that we just read. So we are only interested in the duration column. So these are 3 names of the 3 columns. All right, let's call the duration columns, let's give it a name, right? Let's call it XD, right, for short. Okay, now you can summarize the data using the summary column. So it tells you that the median of the duration is 4, the mean of the duration is 3.576. The variance of the duration is 1.174948. The standard deviation is 1.08395. And let's do a box plot. The box plot of the duration of the eruptions looks like this. So this is kind of really skewed because you can see the box is huge, and clearly the median is not in the middle of the box. So it's kind of a skewed distribution that you're looking at, right? Okay, maybe drawing the histogram might tell you what kind of distribution we are looking at. So let's try to do that now. So hist of XD, as you can see, is nowhere near being symmetric, right? Okay, so here you have the frequency. Now you put frequency equal to false, you get a similar shape, right? Okay, and let's try to change the x-axis using the sequence command. So suppose we go from, say, 1.5 on the left to 5.5 on to the right in steps of 0.25. It produces something like this, right? So the kind of distribution that you're looking at here is a bimodal distribution. Bimodal because you have two different modes. This is the first mode corresponding to short durations, and this is the second mode corresponding to long durations of the eruptions, right? Change this to 0.5, you get something similar. Change this to 0.75, you get this. And change this to, say, 1, you get this. So let's go back to the original one, which is this, right? So as I said, I think this kind of distribution is bimodal, and it is probably result from two different mechanisms mixed together. So the first being corresponding to short bursts or short eruptions, which have a mode around just a little bit less than 2, right? This is the mode of the short eruptions. The second is long eruptions, which has a mode around halfway between 4 and 5, right? So you have two different distributions, one for short durations and another for long durations. And this distribution results as a mixture of the two different distributions, right? Okay. So that completes exercise 2. The third exercise is this one. This is the exercise number 3. So here, this is the Anorexia Data Set. It has these as the four different variables: case number, post weight, and pre-weight, and the treatment. Okay, the weights are in kilogram. And there are 3 different treatments, right? There's a standard treatment and cognitive behavioral treatment. And third is the family therapy treatment, right? And the question here is to see which of the 3 treatments is most effective. And we find that by looking at the weights before and after the treatment, right? So these 2 variables, the post weight and the pre-weight, are crucial, right, to determine which of the 3 treatments is most effective, right? So let's try to do that. So let's go to the website, the course website, which is this one, right? And let's read the Anorexia data set. So this is the data. You have the 4 data sets, the 4 columns, the case number, the pre-weight, the post-weight, and the treatment number, which is 1, 2, or 3. So let's copy the URL and paste it here. And all right, so let's call this data Anorexia, NRE. Okay, so this is the name of the data set. Now, if you type Anorexia, you will see the data that we just read. All right, this is the data that we just read. So the named columns of this data can be seen by typing names. So these are the 4 named columns of the data. Okay, so we are only interested in these 3, right? Okay, so let's see what we can do. Now, in order to see which of the treatment is most effective, we need to first, we need to do 2 things. Let's, just for short, right? Right, let's call this treat. So treat take the values 1, 2, or 3, right? And the second thing we need to do is we need to compute the difference between the weights before and after the treatment. So that's gonna be anorexia post weight, yeah, minus pre weight, right? So this computes the difference. It computes the difference in weights before, before and after the treatment. So that's kind of crucial to determine which treatment is most effective, right? All right, now I'm going to split this data into 3 different data sets. All right, the first one is corresponding to treatment 1. So let's call this DWT when the treatment is equal to 1. Remember, you need to use equal means 1, equal to, right? So, and the second one, let's call this coc.dwt. And the third one is the family one. Let's call it fam.dwt. All right, now to determine the effectiveness of the 3 treatments or to compare them, I'm going to compute the summary statistics for each of these 3 objects. The summary statistics for the first object are these, for the second are these, for the third are these. All right, so this summary statistics tells you, you know, a lot about what happens to the weights before and after. Like here, for the first one, right, treatment 1, it says that according to this, that the mean and the median, the weight hasn't changed an awful lot after the treatment, right? And here, according to these 2 values, 1.4 and 3.007, the weight has changed a little bit, right, after the treatment, all right, but not a lot. It's only 1.4, 3. And finally here, for treatment 3, the median is 9, the mean is 7. And you can see the weight has changed quite a bit under treatment 3, right? So among the 3 different treatments, the most effective one, according to this summary statistics, is treatment 3, right? Because the weight has changed quite a bit, right? Whereas with treatment 1, the change is very, very small. Treatment 2 is not bad, but not awful lot, right? For treatment 3 is quite a bit. I mean, the median, the median of the change in weight is 9, and the mean of the change in weight is 7.265. Okay, right. So this is one way of this is one way of answering the question, right? Another way is to answer this question is using the box plot command, right? If you use DWT tilde treat, this is the plot that you will get, right? Excuse me. So this is a very useful plot. So it tells you there are 3 different box plots corresponding to the 3 different treatments, right? So this corresponds to treatment 3, this corresponds to treatment 2, this corresponds to treatment 1. And as you can see, the treatment 3 has the highest differences in weight, followed by treatment 2, and treatment 1 has the smallest differences in weight. And hence, treatment 3 is the most effective. So doing a box plot like this is very useful to answer questions of the kind in exercise 3. Right, now another thing you can do is to do a histogram. Now histogram for treatment 1 is this. It doesn't tell a whole lot, right? For treatment 2 is this, and for treatment 3 is this, right? And the histogram do not actually tell you a lot. They just tell you what kind of distribution that the differences in the weight has for each treatment, right? But the best way to answer the question in exercise 3 is to do the box plot, which I showed you a minute ago. So let's go back. This is the box plot. So this answers exercise 3 most effectively, right? Because it is very clear from the boxes that which treatment has the highest effect on the weight before and after the treatment. Okay. All right. So this completes exercise 3, and this also completes the tutorial sheet, the solutions to tutorial sheet 3.